Hi and welcome to Unit 1, Topic 3, Video 10, and we're looking at a second proof by induction example that I couldn't fit onto the last video, so here we go. And remember our induction steps, and if you haven't watched video 9, definitely worth a look. So we're going to prove by induction that 5 plus 9 plus 13 plus all the way up to 4n plus 1 is equal to n times 2n plus 3. Very, very similar to the last question. And we take note here that n is greater than or equal to 1 and exists in the natural numbers. So I'm going to start with our obvious place, which is step 1 in the induction proof steps, and that is to prove for n equals 1. So at n equals 1, I get 5, well I get left-hand side is equal to 5. It's just the first term added to nothing. And the right-hand side is equal to 1 times 2 times 1 plus 3, which is equal to 1 times 5, so it's equal to 5, which is equal to my left-hand side. So we'd expect that to work. If it doesn't work, really be careful and check for errors. Now, I'm going to prove, or I'm going to assume that it works for n equals k. Assume for n equals k. And so to assume for n equals k, I'm just going to write down the statement where I swap the n's out for k's. And just make sure you actually don't be lazy and you do write this down. 4k plus 1, k, 2k plus 3. And now I'm going to do inductive step 3, which is to prove for n equals k plus 1. So now I'm going to write this down, and there will be an additional term pop up there, and these k's will change to k plus 1s. So this k will change to a k plus 1 as well, but this term remains. And then I get an additional term with a k plus 1 in it. So 5 plus 9 plus 13 plus ... plus 4k plus 1 plus 4k plus 1 plus 1. And that's now equal to k plus 1 to k plus 1 plus 3. Now what I'm going to do is I'm actually this time going to take the right hand side first. It's the way I really like to do it. And it's not the only way to do it. And in fact, it's probably a little bit less common. But again, I'm looking for that elegance. And I know how summation proofs usually work. So I'm going to start with the right hand side. And then I'm going to head my left hand side towards it in factorised form. So the right hand side can be simplified to be k plus 1 and then 2k plus 5. Because 2k plus 2 plus 3 is 2k plus 5. And then I'm going to get to the left-hand side and see if I can get it to that factorised form. So now the left-hand side is equal to 5 plus 9 plus 13 plus ... plus 4k plus 1 plus 4, well actually I'll spend this, 4k plus 4 plus 1. That helps. Now, I've got, again, exactly the same thing as before, and that is that this is my assumption step here, and that means that it's equal to that thing. So I'm going to swap this thing for that. And now I'm going to look like this. K times 2k plus 3 plus, and I'm going to simplify this, 4k plus 5. So I've done that now, induction step, that I'm working on the induction step, sorry, and I've done the assumption step and substituted that in. Now it's really common. This is classic summation proof by induction. So really be looking for this, and it's how we get rid of that infinite ... term. So now I can't see any common factors here, and I can't get any closer to k plus 1, 2k plus 5. So I'm going to do the expansion and then go back in. So I get 2k squared plus 3k plus 4k plus 5, and this is 2k squared plus 7k plus 5. And Horosho, I'm disappointed because I can see this is going to be one of those real pains to factorise back in the old quadratic world, and I don't really want to. So you might be tempted to just get that and expand it out. But I'm telling you now, you already know what this is equal to. If you've done nothing wrong, that will be equal to this. And I'm not telling you to just jump to the answer, but I'm saying just do a quick check. So if I do a little check up here, I can see my 2k squared. I can see 2k and 5k giving me my 7k, and I can see my 5. So I know it works. I'm just going to write down what it's equal to, factorised. And this is perfectly fine. And if it doesn't work, well then you know you've made a mistake somewhere. This is equal to my right hand side. And then I do step 4, which is to conclude. And I'm not big on writing this conclusion out on a video too often. So I'll remind you that the conclusion looks like this conclusion for our previous question. As the sum works for n equals 1, it also must work for n equals 2. And as it works for n equals 2, it must work for n equals 3, and so on. QED, as required, whatever you want to write at the end to be a bit cheeky. Just keep in mind that this is following the domino anecdote, and that's the idea. So this is like a 5-6 mark question, and there's your solution. Proof by inductions will take a while, particularly step 3, but definitely worth some nice easy marks because it is a very procedural routine approach that you need to follow. All the best.